So it is a calculator day. I would not trust the person that was before you on the calculator. So I would double tap the on key and start a new document. Do not save the old document. Start the new document. Okay. And then we'll be in the graph if you wanted to kick it off of this and put it into the graphs. Okay. So we'll start in there. Okay. So calculators all day today. We're gonna throw stuff. Might throw stuff at you. You never know. Okay. And again, I remind you that we understand that you might not have a graphing calculator at home to use to practice the stuff on the homework problems and things of that nature. But there is a video on Canvas that describes how to solve it in Desmos. On the test, on the formative this week, Friday, and on the test next week, I shouldn't even say next week, Tuesday, on the 16th, you will not be able to use Desmos. You will only get to use the graphing calculator. So when you are going through and we're doing these type of problems, if you have questions or something that doesn't work for you, we gotta fix it right away so you don't keep making that mistake or you get farther and farther behind. Okay? I will stop. I will help you. Okay? Because it might not just be you in the classroom that's having those issues. Okay? So just so you know. But at Desmos for at home, graphing calculators for at school. Okay? So let's start out by graphing this particular parametric function. We are in your note packet by the by. We are in your note packet this entire unit. We put it all together into one. So graph this one on your graphing calculator, then transfer it over into your notes. Should get a circle if you're in radians. If you're not and you only get a little sliver, you're probably in degrees. Okay? So remember to transfer over back and forth between radians and degrees. We just take our cursor, we bring it up to the DEG, and we click that middle button on it. Because you're only going to 2. You didn't go to 2 pi.
Oh.
There you go. You only went to 2. That's all. You were doing the next part that we wanted. Okay. Everybody good on that? Okay. Now, what I would like to do is I would like to play around with the t-values and figure out what happens with said function. So our original function, written as we normally have it, is right here. Okay. Now let's play with that t-step, or let's play with the t-values. So let me come to here, tab. If you hit tab, that opens up the equation portion of it. Okay? And then if you scroll up, it takes you to the last function that you have. Okay? And then if we go down over here. So right now we're at 2 pi. Let's go to something different. Give me something different other than 2 pi. What you guys say? 3 pi. Okay. Can we go to 1 pi first and then go to 3 pi? Okay, right. So let's go to 1 pi first. Now here's the cool thing about this. You can just type in pi if you don't know that pi is down by the key underneath the double E right next to the H down there. That's where pi is too. But you can just type in pi also. And it goes, whoa, what happened to our circle? That's a half, right? Which makes sense. Right? We're all going halfway around the circle. We're only getting half the circle. Okay. Isaiah, what do you think is going to happen when we go to 3 pi? It's going to overlap. It's just going to right over the top of itself. All right, let's check that out. Tab, and then up, and then down. I know, so many different things. Just right over the top of itself. Just keeps going around and around. Well, actually, it shouldn't say around. It went around 1.5 times. If we would go 13 pi, it would go around 6 times, and then a half. Okay. So that's what's going to happen if we adjust that. Now so in trig type functions, okay, where we're in right now, it'll just right over the top of itself. If we were in a function like we had yesterday, where it was like maybe it was a line or maybe it was kind of a parabola of some kind, okay? So if we have some of those, it's just going to expand how far out that function goes. Okay? Okay? So that's adjusting there. Let's go back to 2 pi here. And now let's adjust our t-step. Instead of 0.1 or 0.13, which is pi over 24, by the by, let's go with, I don't know, give me one. 12? All right, we'll go with 12. Jump it up. Row. We don't get anything. How come? What does the t-step do for those people that were paying attention yesterday? Remember? It's how often the calculator calculates it, right? So it calculated it at 0, and if we would look, it would be, I think there's a dot kind of like right there at 0. Really hard to see because it's only one little teeny tiny dot. And then it's going to calculate it again at 12. Well, at 12, we're outside of our t range. So there's nothing to connect it to. So let's go something a little smaller than 12. 2? Yeah, I like 2. 2's a good one. All right? So now what it did is every 2, it calculated it. Okay? So there's the smaller that t-step becomes, the more often that it calculates. Until, that's why we always kind of go with pi over 24, because it's nice, it's kind of the default one. It makes it nice, smooth curve. Okay? Good times. So on this one, let's get to motion. We're gonna start throwing stuff. Okay? Fear not, I will throw stuff. Okay? So we're gonna launch right now. We're just gonna go. We're gonna launch stuff straight up at no angle. Okay? So we're going straight up. What does the ball, or in this case, it's a volleyball. What does the ball, the path of the object, do? Straight up. Then what happens to it as it's going up? Continue at the same speed. Slows down. Why? What's acting on gravity? Okay? Gravity. Okay? Okay? So we launch it up. It goes up. Slows down. What happens? It slows. It slows. It slows. It slows. And what? Right here. Stops, right? And then what? Comes back down. If I was really good at this, okay, average it. We would be in a cylinder, and it would be up and down in that same cylinder, right? Okay? But it's going to stay in that cylinder until something else acts on it. In this case, gravity's acting on it at the top, and it's stopping it. What's acting on it at the bottom? The table, in this case, or ground, okay, would be acting. Okay. Now, there's a couple of things at play. First off, does gravity ever change? No. So that's this part right here on our function. This part right here, this is gravity. Now, you people that are in the physics are probably used to negative 9.8. Okay? But that's meters per second. Gravity constant. We're dealing with feet here. We haven't gotten into the rest of the world in their crazy metric system. We're still on the English feet system. Okay? Right? So that part's gravity. What other effects would happen that would give me the position or the height of the ball that I can use on said ball? What else would affect it? Say loud. How hard I throw it. If I only throw it this much, it's not going to go very high. But if I... The harder you throw it, the higher it goes. Okay? The less you throw it, the less. Okay? That part is this part right here. This part right here is the force behind the launch. Okay. What else is going to affect the position? Trish. The initial height, where I throw it. If I throw it from here, it's going to have a different position if I throw it with the same amount of force than if I throw it from way down here. Okay? They're not going to be at the same spot every time. Okay? And that part comes in right here at the end with my initial height. So we put all those factors together, and we get the motion of a ball going, okay? Or a motion of an object launched straight up. Let's put all that together. Okay? So now we're standing atop a building. We go up to the roof on the third floor, above the third floor. And we're standing there, and we say, I'm going to take this volleyball, and I'm going to launch it straight right at the edge, so that if it, so that it can still go down. Right at the edge, launch it straight up. Okay? Okay? So we can make that function, and that function could be S of t would be what? Negative 16t squared. Gravity constant is constant. It's always there. Plus 50t, because I got to remember my color scheme now. Blue, then green. Okay? Because this right here was my initial velocity, which is there, plus 30, because 30 was my initial height. We were launching it off of a 30-foot. Now, if I type that in regular function mode in my calculator, it's going to look like this. Oops, not tab. Control, page, add a graph. I type it in. Instead of t's, I'm going to put x's. Okay? So because it's in function mode, negative 16x squared plus 50x plus 30. It's going to look like that, and it's going to look like, whoa, wait a second. Ooh, that breaks. I don't like that. I'll just go like this. We'll go here. Menu, window, zoom, window settings, X-min, negative 5. Tab, 5. Oop, that's 56. That's not 5. 5, 1, negative 10. Oh, we got to go up to 80, I think. There we go. That's if I put it in function mode. What don't I like about function mode? It's what? It's not going straight up and down. That looks like it's being launched out. Like I'm throwing it and it's landing over there. That's the downfall with function mode. Okay? Yeah, it's great. We can find a lot of stuff about it. Okay? But we need to come up with here a better way of doing it. And that way is parametrics. So now let's enter this as a parametric equation, because that will model the true position of our ball, or of our object. Okay? So my x value can be anything but 0. Give me a number that's not 0. 1. I heard 1 first. My x position is going to be 1. Done. My y is going to be that height, negative 16. Now, because I'm in a function of t's, I got to switch back to t's, t squared, plus 50t, plus 30. Before we hit enter, let's think about this. What is this number, this 6.28 number right now? What does that represent? The time that the ball's in the air? Okay? Do we think we throw a ball up 30 feet up, down, to the land in 6 seconds? Probably going to land a lot sooner than that, right? All right, let's drop that down to 3. Well, where'd it go? it go? No, really. Where did I thought it just didn't come down far enough. Where did it go? What did I screw up on? Negative 16t squared plus 50t plus 30. Okay? But we don't see the true, we see the true motion of it, yes, but we don't see the whole thing. So we got to adjust our window once again. Okay? Menu, window settings. In terms of x's, I'm okay with it being -3. We'll go to 3. We're going by ones. You can do whatever you want here. -10 to 80 by 10s. And there is our true motion of us throwing that ball up in the air. It would just slide it over. That's all it would do. Yep. If I change it to 2, instead of the red line being here, it's going to be right here. If I change it to -1, it'd be right here. You could be, but see, the reason we do it this way is because we're still old school. In the old school days, we didn't have color screens. And so you only saw one color, and then it just went right over the top of your axes. Yep, that's why we always moved it over. Yes, ma'am? I know what you're saying, okay? And yes, but no, based off of the next slide, okay? So this one is, the parametric is giving you the true position of your object, okay? In a two-dimensional scale, okay? Right? The function, this one, is giving you a relationship of height versus time. So it's just literally graphing the height of your object. Okay? All right? Love it. But what's the problem, man? I'll tell you what the problem is. We don't always throw stuff straight up and down. Sometimes we literally throw stuff at people. Okay? Right? And where you throw it, again, same things come into play. Okay? The height that I launch this at is different than Foxy throwing it back to me. So the positionings are going to be different. I was going to whip it at you with the speed, but I'm not. I'm going to stop. No. Oh, it's knock over your cup. Don't worry. Okay? So the speed at which I throw it is going to differ as to the different positioning. Okay? So to take all of that in, okay? So now, instead of launching it straight up and down 30 feet in the air, we're going to launch it at an angle. What is that? What is the true path of our object? I'll go way over here. What is the true path of our object going to be? It's going to be a parabola. It's going to be parabolic. I almost said parametric. It's going to be parabolic. Okay? The true path is now going to be parabolic. Okay? Based off of our vector, then, I don't think there's anything else down here, we can come up with this. So how we adjust it is based off of the trigonometry of that. You have this on your next little page there. I'm going to go back to this. If I take this initial velocity vector and I make it be a right triangle. Okay? So we're launching it at a 65-degree angle. Then the horizontal part of my vector is going to be, so this is going to be the magnitude of my vector. It's going to be then the cosine 65b over there. That's going to be the cosine, the vector magnitude times the cosine of 65. That's going to be my horizontal component of that. My vertical component is going to be the sine of my angle times my initial velocity. So that's after, let's say, 1 second. After 2 seconds, it would be a similar triangle, right? Right? So it would just be kind of like times 2. Be double that. And so on and so forth. Yeah? So what we do with that then is how we adjust that is we come back with, here is now the horizontal component to your flight, and here is the vertical component. If you put them both together, you get this.
But I think, can the receivers get far enough down the field? Rodgers in trouble. It's going to get there. He turned 32 yesterday. Does he have a vintage moment in him? In the end zone, it is caught for the win. Richard Rodgers.
Nope, I just wanted to mute it. That's all I wanted to do. So I think there's a replay of it then too. So Rodgers threw the ball and he launched it. He had an initial, there's some good reactions on this one. By the way, at this point in time in my house, everybody was sleeping except for me. And right about now, everybody's back awake. I was a little bit loud that night because this was like a Thursday night game. Yeah, it was a Thursday night game. And so it was like 10:30 at night. Anyways, he launches it from here. Okay, he did all the math in his head. He knew exactly, immediately calculated it. He just whipped it. Okay, let's be honest. He launched it from here, so he launched it from like 6 feet. Okay, and his initial height was 6 feet. He had the right angle, which was actually the wrong angle because he threw it short. Okay, but yeah, let's get out of this one. Escape out of this one. There we go. Yeah. From all of this, we can use that and we can figure out so many things. Okay? One of the things that we can figure out is this point down here. That could be how far we throw the ball. We can figure out this point up here, how high, maximum height of the ball. Point over here, total time in the air. We could figure out any position blank seconds into initial throw. Okay? That's how they were able to calculate. I don't know if you heard, but they figured out that like it was the highest thrown ball ever at throw. Like, he almost hit the girders of the dome that they were playing. Okay? Or last year I was at a baseball game in Milwaukee, and they figured out like within 20 minutes that Shohei Ohtani's home run that he hit in that game was the highest ball ever hit at Miller Park. Okay? They can calculate all that stuff based off of what we're about to do. We can do all of those calculations relatively quickly if we know two key things. Okay? Right? Actually, three things. Right? So let's do one. Allow me to introduce you to my good friend, Big Al. Big Al. Big Al. Obviously, some of you know Big Al.
Hi, my name's Alfred D'Elia. At home, they call me Big Al, and I hit dingers.
Big Al hits dingers. Alright? Big Al hits dingers. Okay? Alright? So let's talk about Big Al. It was a couple of years ago. They've been trying to like popularize the Little League World Series, and so they like give all these teams that qualify. They give them like, okay, here's your intro. When you come up to the plate the first time, we're gonna throw it and we're gonna play this, and they are hilarious. Like, look at Little League World Series intros sometime on YouTube. Hilarious. And the teammates behind are sometimes funnier than the person delivering the line. So Big Al hits things. Okay? Right? So he hits a ball at an angle of 28 degrees with an initial velocity of 75 feet per second at a height of 3.5 feet. So let's come up with the parametric equation to model the ball that Big Al hits. Okay? So X is going to be what? $75 cosine of 28 degrees times t. Okay? Y. What's the y going to be? Negative 16t squared plus 75 sine of 28 degrees times t, then plus 3.5. If you would be so kind right now as to parametrically graph that ball flight. But now I don't see the true path of my ball, right? So I got to adjust my window. So if I'm thinking about my window here, I'm thinking -10. How far out do I need to go? The wall's at 190, right? So let's go 220. Okay. How high do you think this ball's going to go? 50 feet, maybe? Ooh, it didn't even barely got over 20. Okay? So there's the flight of the ball that Big Al hit. Agree? Okay? Now, here's the cool thing with parametric equations. Let's build the wall to see if you hit a home run or not. Okay? So my X value for my wall is going to be 190 because the wall is 190 horizontal feet away from me. my y value says that that wall needs to be 4 feet tall. So I'm going to say that that wall needs to be, or y is going to equal t. And then what are my restrictions going to be on t? If I want it to be 4 feet tall, 0 to 4. Put that one on the same graph. So you're going to go into your graph, and you're going to hit tab, and that's going to pop open a brand new function spot. You're going to go 190 there. You're going to go t there. And you're going to go 4 here, and you're going to realize Big Al didn't hit a dinger. Okay? Now, we can adjust the initial velocity to see how hard he would need to hit it in order to actually hit a dinger. So if I jumped this up to, let's say, 79, I got to change it in both spots. But now instead of hitting the ball at 75 feet per second, he hit it at 79 feet per second. Didn't make it. Still not dinger-ish. Okay? Let's go up to 82. We're going up by 3s. So we went up by 4, but getting closer, still no dinger. Go 86. Side note, Rose, guess what the answer is? 86. Does he hit a dinger at 86? Yeah, it barely clears the ball at 86. Okay? And you can quite quickly adjust that one to see when to adjust the parameters of your problem. Okay? With that being said, what I would like you to do now is I would like you to see how far Jordan Love can throw a football. At least get the parametric set up for me. Set the parametric up for me. We'll go through the rest of it. So we should have come up with an x function of 36 cosine of 58 degrees times t. And we should have come up with negative 16t squared plus 36 sine of 58 degrees times t plus 6. Yes? Okay? Now, if we were to parametrically graph that, it's going to look like that, right? The question is asking how far. So I need this horizontal distance out there. Well, one way that we could go about that is we could graph this parametric equation, and then we could trace it until we get out there. But then we got to keep adjusting our trace step to get it smaller and smaller and smaller so that we get closer and closer and closer and more accurate and more accurate and more accurate. Okay? That's one way of doing it. Do I recommend it? Okay. The other way of doing it is we can just graph this y part in function mode. Okay? So if I graph the y part in function mode, I would get something that looks like that. Now that allows me then to solve for this 0, which then I can take this t value, because that's a time that it takes the ball to land. I can take that t value and I can put it into the x part So I could say here x equals 36 cosine of 58 degrees times 2.08773. And that would give me the horizontal distance, because x is the horizontal. That would give me the horizontal distance that I need, which is 39.828 feet. Okay. Now, the nice thing about graphing that one in function mode, the y part in function mode, is that you can then find the maximum height of the ball. Figure out which one it is. You can figure out the maximum height of the ball, and then you can realize that this part right here is your max height. So the max height would be 20.564 feet. I promise we will do more of that tomorrow.